Yes. Good evening to all. Today I am going to discuss one of the important topic in organic chemistry, that is in GOC, General Organic Chemistry, hyperconjugation. 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 So what is hyperconjugation? What are the important aspects hyperconjugation? Now today's class we have to discuss. The hyperconjugation is nothing but to identify stability of carbocation, carbon free radical, and also double bond, that is unsaturated compound. Okay, now we require these aspects to identify the stability of carbocation, carbon free radical, and double bond stability. We require this hyperconjugation effect. So what is meant by hyperconjugation and the applications we have to discuss now. When at least one alpha sp3 CH bond present at alternate position of carbon free radical or carbocation and also double bond Okay, now what I am saying, when at least one alpha CH sigma bond present at alternate position of carbon free radical, carbocation and also double bond, then we have to observe delocalization of sigma bond takes place. Is called hyperconjugation. So I have to discuss with examples. It is better to understand. I go with the example here. CH3 CH2 positive charge. This is the carbocation. This is the primary carbocation. The next carbon we are calling alpha carbon. With at least one CH sigma bond is required. So here 3 sigma CH bonds and also sp3 carbon present. And if you go with the carbon free radical like CH3 CH2 radical. So here also sp3 CH sigma bond is present, and also we will go with the double bond CH3 like CH double bond CH2. Here also we are observing this is the sp2 carbon, actually sp3 carbon and also like 3 sigma CH bonds present at alternate position of double bond, a carbon free radical and a carbocation. Then sigma bond, delocalization of sigma bond takes place. That how it is undergoes, I will discuss now. See here now, this is a sigma bond. This is a sigma bond. The sigma bond present at alternate position of carbocation. Fine. So this is the sp2 carbon. This is the sp2 carbon. It is a planar structure. It is unstable. Comparing this carbon, this is unstable. The sigma bond delocalization takes place. This sigma bond delocalization takes place to here. Why? Because to get the stability, here empty orbital is there. This empty orbital to get the stability. This hydrogen bond, the sigma bond, like the sigma bond delocalization takes place here to here. So then we are observing this kind of structure. That is CH2 double bond CH2. And this hydrogen left here itself by losing sigma bond, it gets positive charge. Same way we are observing here also. Here also carbon free radical. Here also we can observe like this structure. Only one electron transfer takes place here. Only sigma bond with only one electron transfer takes place here. Then we are getting here CH2 double bond CH2 and H radical left over here itself. And also we go with here also double bond. If you take this hydrogen like this, the sigma bond delocalization takes place here to here. Then pi bond shift to next carbon. Then we are getting this kind of structure CH2 double bond CH2 minus. Here this H plus left over here itself. Right? This kind of structures we are observing in hyperconjugation. It is actually two types. That is based on delocalization of sigma bond, the direction of sigma bond, based on the direction of the sigma bond direction and the formation of double bond, we have it is two types, like plus hyperconjugation and also negative hyperconjugation, that is reverse hyperconjugation, right? That I'll discuss. And before that, once again I revise this. When at least one alpha CH3 CH sigma bond, alpha sp3 CH sigma bond present at alternate position of carbon free radical, carbocation and also double bond, then we have to observe delocalization of sigma bond takes place. Okay now, is called hyperconjugation. By using this effect, we can identify stability of carbocation, carbon free radical and also double bond. Right? Now I'll go with the types of hyperconjugations and then applications I have to discuss. Now, it is two types. It is two types. Positive, like positive hyperconjugation, negative hyperconjugation. So positive hyperconjugation, negative hyperconjugation. Positive hyperconjugation already I discussed. This is actually for carbocation, carbon free radical, and also for double bonds we are observing. Positive hyperconjugation. But in negative hyperconjugation we can observe here. It is reverse hyperconjugation. For example, I will take like this, the arrangement like this, trifluoro, which is attached with a double bond like this. Fine. Now here we can observe here fluorine and carbon. Fluorine is more electronegative. So when we are observing this kind of structure, fluorine and carbon is a 2.5 electronegativity. It is electronegativity 2.5. Fluorine electronegativity is a 4.0 on Pauli scale. So please observe here this sigma bonded electrons it will abstract towards fluorine side because of more electronegative. So it becomes partially negative the fluorine, and carbon is partially positive, right? And it becomes like partially positive means like sp2 carbon. So it having empty orbital like this, right? So to get the stability, this pi bond shift towards this side. So here we are getting this kind of structure, like fluoride form here, and remaining fluorine here like this, and double bond over here, and CH2 minus, right? Like we are observing reverse hyperconjugation, negative hyperconjugation. It is also observed in aromatic compounds. We can observe aromatic compounds like this. So please observe here in case of aromatic compounds like this, right? So here fluorine is more electronegative. The electrons, sigma 1 electron pull towards fluorine side, it becomes partially negative, and carbon getting partially positive. To get a stability, this pi bond shift towards this side, then we are getting this kind of structure. Like this is called negative hyperconjugation. We have to say this. So like fluoride ion like this, and here getting positive charge here, and the remaining double bonds intact. So like we are observing positive and a negative hyperconjugation like this, fine. And next I will give one question. Now which of the following compound will give hyperconjugation? Now I will go with few compounds like this. CH3 CH2 plus, right? So this is the sp2 carbon attached to sp3 carbon. This is sp3 carbon, like 3 hydrogens here. So sp3 carbon with 3 alpha carbon hydrogens we are observing like this. If you go with the next CH3 like CH2, double bond CH2. Here also sp2 carbon attached with sp3 carbon like alpha CH bonds we have like 3 alpha CH bonds we have like this. Same way, this is the example 2. If you go with the example 3, like CH3 CH2 minus. See here in this compound, negative charge carbon, that is carbanion, won't give hyperconjugation. And also if we go with this kind of structure, CH2 double bond CH and then CH plus then CH3. Yes, this kind of this structure also won't give hyperconjugation because of resonance effect dominating here. That is the reason why this sp3 carbon hydrogen also won't give hyperconjugation, right? So like we are observing 3 hyperconjugation in this compound. Here also 3 hyperconjugations. Here also 3 hyperconjugation. Here there is no hyperconjugate structures, right? Here also there is no hyperconjugate structures, but it is observed what resonance structures here. Resonance domination takes place comparing hyperconjugation. Fine. So now I'll go with applications. Stability of carbocation or carbon free radical, right? So here please remember one thing here, a number of alpha carbon hydrogens, number of alpha carbon hydrogens is directly proportional to number of hyperconjugate structures number of hyperconjugation structures, and also it is directly proportional to stability of carbocation or carbon free radical. Fine. So more the number of alpha carbon ions, more is the hyperconjugation structures, more is the stability of carbocation and also carbon free radical, and also we can go with the double bond also, right? So now one question here: which of the following compound or structure is more stable carbocation? So I am going with here like sp3ch2, like CH3CH2 plus, and also CH3CH plus CH3, and also I go with like CH3CH3 like. So I am taking these three compounds in this which one is more stable, and also D I am going here, take a CH2 double bond CH, CH2 minus. So the following compound is more stable carbocation. See here, so 3 here, this sp2 carbon, actually sp3 carbon, this is 3, like 3 sp3 alpha CH sigma bonds. Here also, here we can observe this side 3, total 6 alpha carbon ions. Here I think here 3, total 9 alpha carbon ions. Here we are not observing like hyperconjugation structures, but we are observing here resonance we are observing here. Fine. So now in this case, in this 1 2 3 9 alpha carbon ions, we are observing 9 hyperconjugations here 6 hyperconjugations here 3 hyperconjugations here. Fine. Now but the stability order we have to go with the D, then C, then B, then A we have to take. The order is here, order of stability D, C, E, B, then A. What is the reason why D is more stable? Why? Because resonance effect is always dominating than hyperconjugation effect. That is the reason why D is more stable than C, then B, then A. Yes, thank you everyone for listening. Yes.